right, we're going to do the fundamental theorem of algebra. We're on section 6.7. Let's get started. All right, let's get out your note sheets. There's note sheets associated with this. They were something you can download. There isn't really a place that I have you to fill in any blanks, but it would be really good for you to highlight certain things that I'm talking about and put some little notes next to it. All right, the fundamental theorem of algebra. A polynomial function of degree greater than 0 has at least one root. The roots may be imaginary, however. The real zeros are where it crosses the x-axis, and the complex zeros are all of the roots, and those are the imaginaries plus the reals. There is the same number as roots as the degree, and this is the part that's the most important. It's that the degree is the same as the number of roots. This is the number of complex roots is the same as the degree, but you may have the same root mentioned twice or a double root. For example, if you had an equation like this one, where you had the x squared plus 6x plus 9, if you factored that, you'd get x plus 3 and x plus 3. If you set that equal to 0, you'd have roots of -3 and -3. Those would be considered two roots. These are considered double roots, and this is where it bounces on the x-axis. All right, let's talk about those imaginary roots and our irrational roots. Those are considered part of the complex roots, and those are still counted in the part where we had the degree equaling those roots. Complex conjugate theorem tells us that our complex numbers, they come as conjugates, and the roots come as partners. If you have a plus bi, then it has a partner of a minus bi as also the root. So if you have 2 plus 5i, it's got a partner of 2, and the 5i stay the same, but the partner has the opposite sign. So if you have a positive there, you have a negative there. If you had 6 plus 2i, then the 6 and the 2i will stay the same, but instead of a plus, you're going to have a minus, Okay? They come as partners. So if you get one complex root, you have another. Or if you have another, imaginary root, you'll have its partner. Those complex roots come as pairs. Irrational numbers come as conjugates also. For example, if you have 2 plus the square root of 7, you'll also have 2 minus the square root of 7. They come as conjugate pairs, like the imaginaries. Now let's talk about the turns that a graph has. The maximum number of turns that a graph can have is 1 less than the degree. For example, if we have a third degree polynomial, then we're going to have 1 less turns. It'll have 2 turns. 1 turn, 2 turns. So our graph will have 2 turns at most. If we have a 6th degree, then we can have 5 turns. 1, 2, 3, 4, 5 at most. All right, let's do some examples of all those things we just talked about. We're going to do number 1, and we're going to do this with something more concrete than an equation. We're going to actually look at a graph and answer some questions about how many roots, how many possible roots, how many imaginary roots, and so forth. Some of these questions are going to be similar to the ones we had in previous lessons, and then we'll expand upon it. So letter A. Letter A says, or asks, is the degree odd or even? So let's look at this graph, and if you remember, since they're both of the ends are going in the same direction, it's got to be even. Is the coefficient positive or negative? Since they're both pointing up, it's positive. How many real zeros are there? Those real zeros are where it crosses the x-axis, because this right here is the x-axis. So it's 4 times. How many positive zeros are there? Those positives are on this side of the x-axis. And if you notice, there are 1, 2, 3. And there's the negative side is over here, and there's only 1. So if I've just answered 2 questions, there are 3 positives and 1 negative. How many turns does this graph have? Well, when I count the turns, it's like counting the bumps. There's a bump here, a bump here, and a bump here, and those are all turns. There are 3 bumps, 3 turns. If this is the maximum number of turns, what's the degree of the polynomial? The degree of the polynomial is, if that's the maximum number of turns, is 1 more than that one. So this is a 4th degree. Remember, the degree is the same as the number of complex zeros. We said that the real zeros were 4, and the degree is 4. So that means that all of the roots are real and none of them are imaginary. So we have no imaginary roots, because the total number of roots has to be 4, and all of them are real. Let's do another example. Number 4. We're going to do number 4. Same questions. Is the degree odd or even? Since this is going in the opposite direction this time, instead of being even, it's going to be odd. The leading coefficient, is it positive or negative? This is going up this direction and down this direction. So our graph looks like this. It's going uphill from left to right, so it is positive. How many real zeros does it have? It has 1, 2, 3, 4. But this one is a bounce. That means it's a double root. How many are positive? These 2 over here are positive. So there's 2. And these over here are negative, but that one is a double root. We will count it 2 times. So we'll have 3. How many turns does this have? 1, 2, 3, and 4. 4 turns. If this is the maximum number of turns, what is the degree of the polynomial? It's 1 more than this one, so it's a 5th. And that's great, because that would mean that the degree was odd, which we did confirm that. And we got the reals are 5 and the total's 5. So there can't be any imaginaries. So this would have to be 0. Let's do another example. Let's do number 5. Same questions as before. Is the degree odd or even? Since they're going in opposite directions, it's odd. Since we're going up this direction and down this direction, it's going down from left to right, so it is negative. How many real roots do we have? We have 1, 2, 3. 2 are positive and 1 is negative. And how many turns do we have? We have 1, 2, 3, and 4. So that makes us have a 5th degree polynomial. I want you to notice this time that 3 of them are real, but we have a total of 5. So we have to have a total of 5. So if 3 are real, we have to have some imaginary. They have to total up to the 5. Since 3 are real, 2 of them have to be imaginary. Let's now do some more examples. Number 7, 9, and 11. A polynomial function with rational coefficients has the following zeros. Find all additional zeros. If you remember, imaginaries come as partners at conjugate pairs. We talked about that earlier. So it looks like these ones actually have their partners there, but this one does not have a partner. And so we need to find it. We said that the 2 and the 2i stay the same, but instead of a negative, we'll have a positive. That's the only one we have left. Real zeros don't come as partners, but imaginaries do. So I have a 2 and a 2i. Since this is a negative, the other one is a positive. Irrationals come as partners too. So on 11, we don't have any partners for those, but we do have a partner for this one. So -3 and square root 10, instead of the positive, we're going to have a negative. So we found the extra 0. All right, let's do some more. We're going to do numbers 13 and 15. The instructions say, write a polynomial function of least degree with integral coefficients that has the given zeros. For just a moment here, I am going to cancel out of least degree with integral coefficients. And we're going to emphasize the rest of it. Write a polynomial function that has the given zeros. The least of the degrees means that since there's 4 zeros, we're only going to have a 4th degree. All right? If we had a 5th and 6th degree, we could have these zeros but plus extra, but we don't want any extra. We want only those. And the integral coefficients mean we're going to have integers as coefficients and not decimals or fractions. All right. So if we have a root of these, we will have f of x because we want a polynomial function. If I have -5 as one of my roots, then x plus 5 is the factor. If I have 0 as a root, then x is the factor. If I have -2 as the root, then x plus 2 is the factor. And if I have 1 as a root, then x minus 1 is the factor. And so our goal now is to write all this out. Since it said that it wanted integral coefficients, it actually wants coefficients and not just a bunch of factors. So we need to multiply this out. So what I'm going to do, I'm going to take these two right here, and I'm going to multiply them. Then I'm going to take those two and multiply. Then we'll take the product and multiply that together. So let's do x times x and x times 5, which is going to be x squared plus 5x. Then we're going to multiply this out, and we're going to go x squared and -1x and 2x and -2. These are like terms, so let's bring them together. Now we have to multiply this together. We have to multiply the x squared to everything and the 5x to everything. So I do the x squared, I'll get x to the 4th. I kind of like to do them up and down. X to the 4th, x to the 3rd, and -2 x squared. Then when I do this one, I'm going to write them under their like terms. That's going to be 5x to the 3rd. And I wrote it here because they're like terms. That will be 5x squared, and I'm going to write it under this. And then this is going to be minus 10x. Bring this down. We're going to just add now. X to the 4th plus 6x to the 3rd plus 3x squared minus 10x. We need to put that f of x at the beginning. All right. There is our polynomial for number 13. Let's do number 15. All right. We have 2 roots. But this one has an extra one to go with it. So this one has -1 plus I also. So we have f of x that is our root, so x plus 2 is my factor. If this one is my root, then x minus all that is my factor. So then I'm going to distribute that to those, and I'll get plus 1 plus I. And I'll have x minus those, which when I distribute it will be plus 1 minus I. Now I have to multiply this out just like I did before. But I'm going to multiply this one first because it's going to be something really cool when we're done. So I'm going to just rewrite this f of x and my x plus 2. And this is going to become x squared and x and negative xi. This is going to become x and 1 and minus I. And then I still have the I times the x and the I and the negative I squared. Okay, there's a lot of things that cancel out here. All right, so this xi with the negative xi and positive xi, and this negative I and that I cancel out. These are going to come together, and I squared is going to change. I squared is going to be a negative 1, and that already negative makes it a positive 1, so this makes a plus 1. Let's bring all this together. F of x equals x plus 2 times x squared plus 2x plus 2. We're not done even still. We need to multiply that out. We're going to multiply x times x. We get x squared to x cubed. We're going to get 2x squared and 2x. I'm going to write things underneath, so I think it's a little easier than we did when we did it all out. The 2 times the x squared is 2x squared. The 2 times the 2x is 4x. And this is going to be plus 4. Add it all together. Don't forget our f of x is going to be x cubed. Adding these two together, I'll get 4x squared. Plus this will be plus 6x. And then plus the 4. And we're done. Let's do number 17. We're going to answer all these questions. This is very similar to what we were doing with the graphs, but now we're going to do this with just the equations. We learned that the degree is the same number as all the roots, and all the roots are the complex roots or the complex zeros. So the degree is the same as the complex zeros. The degree of this is a 4th degree because that's the highest exponent. The possible number of reals. The possible number of reals for a 4th degree, we can kind of look at this graph. It's going to be an even degree, so we know it's got to start up and go down, and it can have these bumps in it. It can have 3 bumps if you remember. So the total it could have is 4, but that would make total sense. It could have 4 because we know it's the degree. It's the degree, so it can have 4, and then it goes down by 2 for the same reason it does for those positives and negatives. So it can have 4, 2, and none. The possible number of imaginaries. Well, can a 4th degree equation have all imaginary roots, meaning no reals? If I had the x-axis here, could I draw a 4th degree that didn't cross at all? Yes, I could. So it could have all 4 being imaginary. They come in partners, so we have 4, 2, and 0 also. Now the possible number of positives and zeros, remember those are the sign changes. And so we did the sign changes in the last unit. If we have a positive here, we have a positive, a negative, and a negative. We have one sign change. So that is the number of positive zeros. So I'm going to put a positive and put a 1 next to it. Now let's do the negatives. Now the negatives, if I'm plugging a negative 1 in for x, it changes if I have an odd degree, but not for an even. So they don't change at all for the negatives, and I have one sign change again. So negative roots, I have 1 for both of those. The possible rational zeros are the p over q's that we were doing last time also. P over q is the roots of 18, or the factors of 18. We have 1 and 18, 2 and 9, and 3 and 6. And all the plus and minuses are those. And then q is the factors of the numerator, which is plus or minus 1. And when I divide everything by 1, they just stay. So the nice thing about this one is I don't even have to list that. This is all the possible rational zeros. 1, 2, 3, 6, 9, and 18. All the plus and minuses of those. Now, it wants us to factor this. So we could do this in multiple ways. We could divide it by any of these possible roots right here until we get a remainder of 0. Or we can look and see if it's a form that we're used to. And this looks like it's a quadratic form because that's 4 and half of it's there, and it's a trinomial. So I'm going to factor it using that method, the box method. I'm going to have x squared and x squared. What multiplies to be 18 and subtracts to be 3. 6 and 3, and I need one of them to be negative. And so we want it to be add to be negative 3, so I'm going to have to make it that. All right, so my factors are just straight across on the horizontal there. So we have f of x equals x squared minus 6 and x squared minus 3 plus 3. So we're going to find the zeros of this for the next letter G here. When we're finding the zeros, it means we set it equal to 0. That means I set each of those equal to 0. So we're going to have x squared minus 6 equal to 0 and x squared plus 3 equal to 0. We're going to add that 6 to the other side. We'll have x squared equals 6. Take the square root, and we'll have x equals plus or minus square root 6. Now we're going to do this one. We're going to subtract that 3 to the other side, and we'll have x squared equals negative 3. Take the square root of both sides. Since we have a negative, it means we're going to have an imaginary. We took the square root, so we have a plus or minus. We have I squared root 3. Here we're going to write plus or minus I squared root 3. I want you to notice we said we had complex zeros. That's all the possible zeros there can be because it is a 4th degree polynomial. And we have 1, 2 there and 3, 4 there. Let's do 18 now. We have a 5th degree polynomial. If we have a 5th degree polynomial, that means that the highest exponent is 5, so the complex zeros are 5. The possible real zeros. There are 5 possible real zeros. There are also 3 possible real zeros and 1. It can go down by subtracting 2. The possible number of imaginary zeros. So this is going to at least cross one time. It has to at least cross one time because when we have an odd degree, we're going to have one going up and one going down. And it could curve in the middle, so it's at least going to cross one time. So if we have one real, we can only have 4 imaginaries. And we go down from there. All right, how many possible positives and negatives can we have? That's when we do our sign changes. So I have a positive here, a negative, negative, positive, negative, positive. And so I have 1, 2, 3, and 4. So 4 positive possible zeros, or 4 positives. And now we're going to do negatives. Now negatives, we switch them when they're odd. We keep them the same when they're even. So I keep this one the same. And I switch the others. Since it's positive here, I switch it to negative. I switch this one to positive. And I switch this one to positive. So we have one sign change for the negative. So we have one possible negative 0. All right, the rational roots, this is the P over Q. So P over Q, P is the the factors of 45. So that's going to be 1, 5, 9, and 45. Because 1 times 45 is 45, and 5 times 9. And we have all the plus or minuses of that. The Q is the coefficient in front of the leading coefficient, and so that's plus or minus 1. The cool thing, again, just like over on 17, is we don't have to do all the fractions because 1 is just it. So our answers here are plus or minus 1, 5, 9, and 45. Let's now factor this. Now, this we could do division with this, or we could look and see if it's some kind of form that we're used to. The forms we had before was factor by grouping. Is it a quadratic form? At first it doesn't look like a factor by grouping, but if you look at it, if I group this one and this one and this one together, can I take something out of this? I can take it at x to the 4th out of that. I can take out a 2x to the 2nd out of that, and I can take out a 5 out of that. Will I get the same thing? Let's check. So if on this one, if I took out an x to the 4th, I would have x minus 3 left over. On that one, I have a negative in front. So if I take actually a negative 2, x squared out, what's left? I'm left with an x, and since I'm taking a minus out, that'll become a minus 3. Oh, wow, look, those are the same. That's what we're looking for when we do factor by grouping. One more thing. When I do this one, what can I take out? I'm going to put that negative right there, and I can take a 5 out. When I take a 5 out, what do I get? I'm going to take out a negative 5, really, and I'm going to have a 3 there. Oh, 3. An x. Actually, I'm not going to take a 5 out. I'm going to take a 15 out, and I will be left with an x. And then take a 15 out of that, and a negative 15 out. I'm going to have a minus 3. Oh, wow, look at that. I've got an x minus 3 there in all of them. So if I have an x minus 3, and I take it out of all of these, I will have what's left over. I'll have x to the 4th minus 2x squared minus 15. This is a quadratic form like that one, and we can do a box method. But I'm running out of room. My box method over here says I'm going to do x squared and x squared. 15. What multiplies to be 15 and subtracts to be 2? Is that 3 and 5? Yes, it is. And I need one of them to be negative, and that negative needs to be something so that I get a -2 when I'm done. So it's got to be that one. And we write them as the horizontals. So I'm going to bring down my x minus 3. X squared plus 3 and x squared minus 5. We have now factored this. So this is my answer for letter F. Let's now find the zeros. That means we're going to set this equal to 0. And solve. That means we're going to set each piece equal to 0. To solve, we add the 3 over to the other side, and we get x equals 3. We subtract the 3 over to this other side, and we get x squared equals -3, square root both sides. And we get x equals plus or minus I squared 3. We'll write these up here at the top. And the last one we have over here, we're going to subtract that 5 to the other side, and we're going to get x squared equals 5. And we'll get plus or minus square root 5. We have a total of 1, 2, 3, 4, 5 roots. And that is exactly how many we were supposed to get. This one's real, and that one, those two are real. So we have a total of 3 real, and we have 2 imaginary. All right, this lesson we learned a lot. We learned that the degrees is the same as the zeros. We learned that imaginary roots come as partners. We learned that irrationals also come in partners. Those partners are called conjugate pairs. And we learned that the number of terms added to 1 is the same as the zeros. That's the maximum number of terms. I hope this has been helpful. Goodbye.